All right, everybody. This is a very important topic whenever you talk about an enzyme, and that topic is enzyme inhibition. As a little bit of preface, many substances bind to enzymes and decrease the velocity of the enzyme catalyzed reaction. These are known as inhibitors. Okay, enzyme inhibitors are important for a number of different reasons. They can be used to gain information about the shape on the enzyme active site and the amino acid residues present in that active site. So you can learn a little bit about what are the interactions that take place between a molecule and an enzyme, or a small molecule and an enzyme's active site. They can be used to gain information about the chemical mechanism by which an enzyme catalyzes a reaction. So the order of substrate binding or product release and formation of any sort of intermediates along that pathway. They can also be used to gain information about the regulation or control of a given metabolic pathway. So, is an inhibitor going to, or an inhibitor is going to be able to give you that sort of insight of the overall pathway or, certain steps within that pathway. And they can also be very important in drug design. So enzyme inhibition follows a couple of different methods, one of which is an inhibitor can be reversible. So that means that a substance binds to an enzyme to inhibit it, but it can ultimately be released. This usually involves formation of non-covalent bonds. So you have an ionic bond or a salt bridge formed between an inhibitor and the enzyme active site. And this is going to generally result in two different categories of reversible inhibitors. One is a dead end reversible inhibitor, and the alternative is a product. So typically, a product could actually be generated. Typically a compound that is not a part of the normal reaction, but looks like either a substrate or a product, when it binds, it stops the reaction or causes a actual dead end to it. Okay, so the alternative type of inhibition is an irreversible inhibitor. And that could be displayed by a substance that causes inhibition that cannot be reversed. So kind of counter to your reversible inhibitor, this is going to be one in which the formation or breaking of covalent bonds. Okay, so if you want to kind of go back to Gen Chem 1, you could think about this as are covalent bonds being formed or non-covalent bonds being formed. With a reversible inhibitor, you have non-covalent bonds and non-covalent interactions, whereas in an irreversible inhibitor, you have covalent bonds that are either being formed or they're being broken. So inhibitors act in a number of different ways, in a number of different mechanisms, and this is kind of the most visual component of this material because you have graphs that you can directly associate with it. Now, an inhibitor may bind at the same site as one of the substrates. These inhibitors structurally resemble those substrates. Okay, an inhibitor may bind at an alternate site, affecting the catalytic activity without affecting substrate binding. But there are many inhibitors that actually do both. And if you want to think about this from kind of a design standpoint, you could think about it as, well, what do I want? What would be the best outcome? If I want to completely render this reaction non-sustainable, but I want to make sure this reaction never takes place again. What's your best way? What's your best approach? Well, you can kind of think about it as you've got a two-pronged approach. You could either disrupt the substrate binding, or you could disrupt the actual velocity, so not disrupt the substrate binding. But you could also do both. Okay, so your most common types, and that's all of these different examples are going to be explained in just a moment. Your common types are a competitive inhibitor, a uncompetitive inhibitor, or a mixed and a non-competitive inhibitor. And I bring this term up, a non-competitive, because it's kind of because it is a terminology that you will see from time to time. But over the years, non-competitive has kind of been a little bit diluted out in favor of discussing this type of inhibitor as a mixed inhibitor. So you'll hear mixed / non-competitive inhibitor from time to time. So use those terms a little bit interchangeably. Okay, so now your inhibition patterns. A competitive inhibitor, well, this is one in which a substrate is going to compete an inhibitor is going to compete with a substrate for the enzyme's binding site or the enzyme active site. And so you'll see something like this. Well, you're talking about the free enzyme binding with your either substrate or your inhibitor, and you're either going to form this EI complex or this ES complex. Now, if you have the enzyme bind with the substrate, obviously that's going to form that ES complex. If the enzyme binds to the inhibitor, then you're going to form an EI complex, in which case that EI complex is not going to be able to interact with that free substrate, in which case no reaction is going to take place. Now, I would like to draw your attention to this right here, this Ki. Think about your Ki as being analogous to your Km, and it does say something about the affinity that your that your enzyme has for your inhibitor. But I'd like you to look at this because this is a constant and this is reversible. So binding of the inhibitor, well, it could release it. It depends on the actual interaction between that enzyme and that inhibitor. Now, an uncompetitive inhibitor, well, that's going to bind to the enzyme substrate complex, but not to the free enzyme. And so we'd see that displayed like such. So I'm going to draw an arrow right here. Uncompetitive inhibitor, your enzyme plus your substrate forms that ES complex. No problem there. So that initial step, the formation of that ES complex does take place. But in the case of an uncompetitive inhibitor, well, then you're going to have this ESI complex form. That ESI complex shows the enzyme substrate and the inhibitor are going to bind together, in which case you're going to have no ultimate reaction. So this K2, this progression from ES to your product plus your enzyme, that's not going to take place because it's kind of being like diverted, or your enzyme substrate complex is being diverted away from actually forming that product. Now, the last type of inhibition, or that last pattern, is that mixed inhibitor. And that's going to be an inhibitor that binds to both the free enzyme and the ES complex. And that will be displayed with this graph down here, or this kind of flow down here. E plus S yields ES, or, well, this type of inhibitor can bind to the free enzyme, in which case you'll go here, which is just like a competitive inhibitor, or, well, you can have this inhibitor bind to the ES complex and form that ESI, in which case that is also going to produce no reaction. So in both of these cases, you have an inhibitor that is going to interrupt this reaction and no reaction is going to take place. So this is an important thing to think about and an important thing to sort of explore, because basically what a mixed inhibitor does is it kind of has the best of both worlds. It's able to bind to that free enzyme, or it's able to bind that ES complex. In both cases, if it does, well, that is one molecule, and that is inhibiting this reaction in basically two different ways. Okay, so now how do we distinguish between these different types? Well, the easiest way is to make an inhibition plot. And so what you're going to see is if you have a graph that shows a variation, a Lineweaver-Burke plot that actually kind of deviates whenever you add an inhibitor, that's going to give you a little bit of insight. So the pattern of that graph is going to tell you what type of inhibition. We're going to get to those in just a second, but it's important to think about this because of the fact that, well, we become so accustomed to looking at the graphs and saying what type of inhibitor it is. You have to remember the way that this is approached is from like the scientific method. You would gain some insight, maybe from a structural study. What does this protein actually look like? Okay, I'm going to design this small molecule, and I would expect that it's going to bind in this particular location. And I expect, because it binds in that location, maybe it's going to be a competitive inhibitor. Well, that's all good and well, and that's a great approach, but ultimately what matters is what does that graph actually look like? Because when you look at that graph, that's going to tell you what type of inhibitor it is actually functioning as. So it's a little bit backwards, but we get this is a little bit backwards because we get so accustomed to looking at the graph and saying what type of inhibitor it is, rather than thinking about it from, well, you have to design the inhibitor, study the inhibitor, then develop the graph and say what type of inhibitor it is. But essentially, these are your three major types: your competitive, uncompetitive. I'm going to make a little dot by them: competitive, uncompetitive, and mixed. Um, and it's these three different, basically, schematics that show you essentially what's happening. Okay, so this Ki is an equilibrium constant of the inhibitor binding to an enzyme. Ki is important because, well, it tells you a little bit about the affinity that an enzyme has for an inhibitor. The affinity that an enzyme has for a given inhibitor. How can we determine it? Well, we can determine it by analyzing the slope, the y-intercept, and x-intercept in the presence and absence of inhibitors, and that is what's going to allow us to determine what our Ki is. Okay, so our Ki is going to be mathematically expressed by this equation right here. And that is your Ki is equal to your inhibitor concentration divided by R minus 1. Now that R value is not your gas constant or anything like that, but your R value is something that's going to vary. So when you investigate and you have the different graphs of a competitive, uncompetitive, and a mixed inhibitor, you will be able to determine, well, what is my actual R value? So this table down here shows you how to calculate that R value. So in the case of a competitive inhibitor, your R value is equal to your slope with the inhibitor divided by slope without the inhibitor. Or you can use the Km apparent, so the Km with your inhibitor divided by your Km with no inhibitor. Okay. The uncompetitive inhibitor R value is going to be your y-intercept with your inhibitor divided by y-intercept without your inhibitor. It's also your x-intercept without or with your inhibitor divided by x-intercept without inhibitor. Then finally, if you believe it to be a mixed inhibitor, you are going to take your R value of your slope with your inhibitor divided by slope with no inhibitor and set that equal to, or you can use y-intercept with your inhibitor divided by y-intercept without the inhibitor. And we'll do some practice problems related to this and actually come up with what is the Ki. But that's all I got for this. I would recommend becoming very familiar with those different graphs. That's going to be very helpful, with those three different definitions, three different types of inhibitors, and then look at the different graphs, which we will do in just a moment. All right, well, thank you very much.